Everyone will start in 2 minutes or so. We will record it as well. Everyone will start in a minute or two. Let everyone join. Okay, everyone, so let's start. I'm going to record that just in case. We have here Kevin Toops from WECA CTO office that's going to present to us the IO500 task. Kevin, stage is yours.
All right, thanks a lot. Welcome, everyone. This is the IO500 task for the ISC-25 student cluster competition. And we're excited for WECA to be a sponsor. My name is Kevin Tubbs. I'm the field CTO for HPC and AI at WECA IO. So first, we're going to talk about some trends in HPC and AI. There's three big areas: the compute, the networking, and the storage. And we're going to see these trends and why we think the IO500 is important for the student cluster competition. So on the compute side, modern compute has been dominated by GPU acceleration and other accelerators. We're seeing like a 10,000x versus traditional CPU only. Back in 2008, the top 500 supercomputer first place was a 1 petaflop system with 10,400 rack units. Where you fast forward that now to last year, 2024, this was dominated by an NVIDIA system, DGX GB200. It was 42 rack units and delivered 1.4 exaflop. So we're seeing this drastic increase in compute. Another trend that we're noticing that's driving this is modern networking. We're seeing over 100x improvement in versus a legacy. So if you look back, 2002 standard was 10 gigabit. Probably on a single port, you're looking at 32 ports and 266 hosts. So size of systems. Where if you fast forward to 2024, moving more to ConnectX 8. So this is InfiniBand and Ethernet going to 800 gig. And you're looking at single switches with 144 ports at 800 gigs, as well as 5,000 on the order of 5,000 hosts on spine leaf architecture. So drastic improvement there. What does all of that lead to? For now in supercomputing, we kind of look at it as a infrastructure triangle. A lot of the performance of the systems and applications depend on balancing the compute, the networking, and the HPC and AI storage. So how those things are put together efficiently determine how well a system or an application performs. So we're going to talk a little bit here about what Weka does, and then we're going to talk about open source parallel file system that you'll be using or have available to use in a student cluster competition. Traditional Weka deployment generally looks like this. You see at the top just our application layer, different applications. You want to put, design a HPC infrastructure to run for different applications and different storage. So at the top, you just see the different types of clients. Some may be GPU, some CPU, different protocols, but this is kind of what we see across different systems. And then at the bottom, you want a file system that provides a global namespace. In this case, it's WECFS, which we are software defined. So we run on any industry standard x86 servers. So really, that's kind of talking about us and how we set up. But you can look at this and keep this in mind when we look at the other open source parallel file systems. You're going to have your application layer, your client and compute layer going into a network attached storage. And that network can be InfiniBand or Ethernet. But the key is you always want a high speed network for that storage access. So another thing, when you put that, here I'm going to kind of look more in the context of AI because it's a hot trend. But basically, you want that data or that storage system to be able to look at or handle a lot of different workloads. So what you see here is just the kind of the data pipeline for a AI workload. But as you look at the top, there's different characteristics as you go from workload to workload, or specifically application. On the left, you see a natural language processing pipeline. The sequencing pipeline is more of a HPC genomics, computer vision AI pipelines. Then you have some traditional HPC and high performance data analytics pipelines and generative AI. But you see in each different case, the IOPS and bandwidth may change, the file sizes may go up and down, the read-write performance will read to the left, write to the right, and number of files. So the key thing to take away of this varies a lot based on the application. And depending on the vertical or field, there's a lot of different protocols from GPU Direct, NFS, POSIX, S3, SMB, or HDFS. So that's kind of what we see from serving HPC systems. So next, we're going to look at what you probably be using in the student cluster competition, what you have available to you, are open source parallel file systems. You want those because they're usually scalable, high performance, provide data for the different workloads. The other key thing that you see in most open source parallel file systems that the distributed data across multiple servers and multiple devices. So what you'll see in common in all of them, they're software running on Linux servers that basically take the compute and the storage devices and network and turn it into a file system. So key things, scalability. You want to be able to scale that. High performance, you want to be able to have high bandwidth, high read-write capability, high metadata performance. And then the other key is shared access. So when you're working on a cluster and you need to be able to read and write through the application or access the files, you need to be able to access the data from the different compute nodes. Other things, fault tolerance, we're not going to cover that, or it's not going to be part of the competition, but it's important that you can actually keep the data and keep access to it. And the other key is global namespace, that you can actually access that data from each one of the clients, or in your case, your compute nodes. So here are some examples of the open source parallel file systems, and these are all ones that you can design and download and install on top of your, as part of your student cluster competition. So one of the most traditional, long-standing ones is Lustre. Large adoption in many HPC clusters and supercomputers. We also have BGFS. This is a more recent or modern software-defined open source parallel file system as well. It's also known for its easy use and scalability. It also works well for HPC, AI, and ML. We have parallel virtual file system, which is now OrangeFS. This is a little bit older, but it's still a good open parallel file system for large scale cluster computing and HPC. Another option is MooseFS. This is a distributed file system, mostly on fault tolerance and scalability. Another option is DIOS, and that's distributed asynchronous object storage, originally created by Intel. It's a parallel file system for high performance computing and artificial intelligence workloads. This is one of the newer ones. And then we also have NFS, which is network file system. This is a distributed file system, and it's kind of more common and built into a lot of the Linux stacks. So you're able to, I think the most simplest is to set up an NFS and use that as your shared storage. So there's a lot of things to be able to do that. But of these examples, I think kind of an unbiased for terms of ease of use and performance, I'd look into BGFS. But all of them have options that should be able to run on the size of the minimum amount of nodes required should be on the order of what you're using in the student cluster competition. So BGFS can be installed on, I think, a minimum of 2, but all of them should have a minimum nodes of 2 to 4, so you can be able to run this on your cluster. I think another benefit of BGFS, and I think DAOS as well, they're able to run alongside of your compute application. So you can able to run it and serve it on the same nodes that you're doing the HPC on. So that's a summary of your options for the open source parallel file systems. So now we're going to talk about the task itself. What is the IO500? So it's a benchmark suite that's composed of IOR and MD tests as applications. IOR has different variations, so they can run an easy test, hard tests, and then there's variations of the MD tests or metadata tests that are easy and hard. If you look on the left, basically there's on the y-axis namespace complexity. So how there's going to be an IO pattern that's performance based, but also encompassing the entire file system. And then you're going to have some data pattern complexity on the x-axis. So this is kind of how it creates a map. So you want a suite of storage benchmarks that mimic the different things that happen during an application. So IOR easy test. This is mostly a efficient bandwidth and IO pattern test. This is used during most HPC procurements to find out, how fast or how much bandwidth the storage can provide. IOR hard is a same IR test, but we're going to use a single shared file. So you're actually performing multiple processes on a single file. So the combination of these two let you understand how the same storage system behaves under different bandwidth characteristics. The MD test easy, basically metadata test to create ranked directories within empty files. This small IO, small file type of creation is one of the things that an application does that creates files intermediate. You see this a lot in life sciences as well, but anytime they need to create intermediate files and things like that. So this is a test of being able to do that. MD test or metadata test hard is a single shared directory of small files. So these are 3901 bytes, and it's a POSIX interface. So again, this is testing the storage capability to create and operate on small files. And then the find functionality searches for files of the same thing, small files of 3901 bytes across all the created files. So this kind of gives an example of the different capabilities or different types of tests in IO500. And the goal is to kind of create a storage performance space for the same file systems and measure them all against that specific case. And all of this are primitives that should, mimic what you see in the application. So why do we have the IO500? So with the increase in different domains and verticals that are using it, a lot of the trends, especially with AI, larger data output, larger data input. So it's putting more stress on file systems. Researchers, customers used to only buy storage based on the max throughput gigabytes per second achieved by our, but the applications may not actually be able to perform that way. So you need to have a benchmark or suite to understand the real performance expectations. And these are only primitives because different commercial applications and different research applications perform differently. So you want to be able to track the storage performance and best practices across a bunch of different use cases. How? So this is the IO500 is a community-driven effort run by nonprofit organization. It's run through discussions and mailing lists, Slack, etc. Everything is managed and published on the GitHub, shown here, but we'll kind of go through that. The patterns mostly around metadata performance, data, bandwidth and movement, and search capabilities. We rate the easy based on optimized patterns, and hard tests are based for complex patterns. The whole suite relies on community benchmarks, primarily IOR and MD tests, which are packaged and built within. And we'll go over some examples of that. So how to run the IO500 tasks. Basically, we're going to go over the preparing and building. Then there's going to be some steps to run it, review the results, and then you're going to submit the results at the end to the student cluster competition committee. So in preparing and building, it's just a simple 3 steps. You're going to git clone, pull down, you're going to cd into that directory, and then you're going to run a file called prepare.sh. Now, as long as this file has, long as you've already installed and set up your cluster, so you want to already have MPI and your message passing installed, a lot of the prepare is going to be based on what is your parallel compiler, so which version of ISC-SCC and things like that. But as long as all of that is already installed on the cluster, should be really simple to run that script, and it'll build everything, and you'll be able to run it entirely in that directory. So the steps to run the IO500 for the competition. So you're going to modify the existing IO500.sh script that comes with when you check it out at GitHub, and it includes information on running the MPI jobs directly or with a job scheduler, and I'll go over that a little bit more later. There's also a config file. This is what you use to kind of change parameters, but in this case, the entire competition, we're going to use a committee provided config ISC-25.ini for the competition, and this will be provided on site at the competition. This file is usually, like I said, used to modify and tune how you're going to run and fine tune. But because it's a limited competition, we're going to all use one file. But also in there in config files, there's a test configuration that's called config-debug-run.ini. This should be used to make sure that you have everything set up. It basically creates a 1-second run. So you stonewall all of the things to run for 1 second. And it doesn't take a long time to finish, but it lets you get through every test. And note that the results will show invalid, but it's useful to know that you can get through the whole thing and you can see what your output looks like. So again, we recommend using config-debug-run.ini to test your setup. Once you set the IO500.sh and you have the specific config file, you want to execute it with IO500.sh and pass it a config file. You can do that directly or via batch submission, sorry. So in that, you're not going to go through, you want to review those results, make sure you have valid. It'll make more sense later. And then we want to be able to submit the results before the end of the competition. So I'm going to do a demo, try a live demo, but basically it's easy to build, should be less than 70 seconds for the basic version. I'm going to escape out, go here. So here I have my directory, and here I can run the git clone. So now if I do this, you'll see I have IO500. I'm going to cd to IO500. I'm going to do ls just so I can see. And then here, prepare.sh, and should take less than 70 seconds. I think I did it. And it took less than 30 seconds, but it's just going to build and check for everything, build it out. And you should see if you have some issues, but it shouldn't be a problem. And I'll show you what the completed version looks like. When you get to the bottom, it'll say, okay, all required software now prepared, IR, and that's all it took. Whoops, sorry about that. All right, so now we're back here. All right, so modifying the IO500.sh. So the variables there are the MPI run and MPI arg. So you want to look at what commands you want to run your MPI job. Is it MPI run, MPI exec? And then you're going to use the MPI args variable to pass any MPI argument. An example you have below, I'm passing to specify which interface to make sure I'm using the right interface. I'm using map by nodes in my host file. In this case, number of processes is 60. But basically, however you would run it directly or bash, you want to put these arguments for what the MPI run command would be and what the arguments would be. The other thing inside of, and you can look at it and go through it, the setup section at the top, you can use that optionally. You don't need to use it. But this is how you would use commands to create top-level test directories under the work directory. So if you wanted to do anything like striping different folders or things like that, depending on which file system you're using, that's about the only thing you can do. But again, that's very optional. You don't need to do it. Really, the only thing you need to focus on, what is my MPI run command, and what arguments do I want to pass? In this case, I have a host file. That host file has to be there, and it's going to describe my cluster. Reviewing the config -ISC-25 INI file. So again, this is one that you're not going to modify. All teams will use the same configuration file. Here I have some examples of like what it looks like. So there's a debug flag, and their stonewall time equals 200. So that's 200 seconds. That means that for the write performances, they're going to make sure that it doesn't run too much longer than 200 seconds. So once it passed 200 seconds, it's going to start initiating shutdown commands. So when you look at a write test in your run, it should be longer than 200 seconds, but it may end up being 205 seconds, 215, because it shuts down after 200. And then you look at each individual test case. There'll be some that are run, and that means run equals true. And then there's some that will be skipped by committee design for this test, and you'll see run equals false. But again, you can look at these, but do not modify, and everybody runs the same config file. So for a valid submission on your run, you need to execute all the tests from here, which will be 6. And the right phases of those tests need to take at least 200 seconds. We've run this on multiple different situations, so they all should run longer than 200 seconds. So it shouldn't be a problem. So this is an example of the output of the results underscore summary.txt from an IO500 run, and this is a complete. So this is if you were running it on a full system, not using the ISC-25 config. So you see here, you get an example for every test. You get a result, you get the name of the test, you get a performance number, which will be in either gigabytes per second or kilo IOPS, and then you have a runtime here. And then at the end, if everything completes, you'll see score. It'll give you a bandwidth score and an IOP score and a total. So the bandwidth is going to be a geometric mean of all of the bandwidth tests. The ops is going to be a geometric mean of all the IOPS tests, and the total is going to be a geometric mean of these two. So more to the config files that you'll be using, your output will look similar to this. So you don't want to be concerned with invalid flags on tests that were false. You can tell that a test was false here. They're highlighted gray because you get a performance of 0, which means it didn't run, and a runtime of 0. So anytime you see a result with 0 performance, 0 runtime, and an invalid, that's okay to ignore. Of the ones that we are running, you should get a, these are ones that are not grayed out. You get a performance, you'll get a time, and then you'll get a final score. If it runs to completion, you'll get a final score. Your score will say invalid, but this is one you can ignore, and I'll talk a little bit more about that. So if we look at submitting the ISC results, you want to review your output and verify that none of the required results, the results are going to be in $result directory because it changes every time that you run it. And the main one we're going to look at is result underscore summary.txt. So you want to make sure that your required tests, the ones down in gray, don't show invalid. They would do that either because they didn't run 200 seconds, which shouldn't be the case, or you had some other error in the run. But at the end, you should get something with these 6 results at the bottom. So if you're inside the config file was marked true, it's going to give you a valid performance. That time is going to be, for the write, it's going to be greater than 200 seconds. And the reads can be less than, but that'll be fine. If you see the invalid on performance results are 0 and time is 0, ignore those. But the key thing is it has to run to completion, and you know that because you'll have a score at the bottom. So again, here, when you have a score, if I have these 6 with valid results, you're going to get a result here. This is going to say invalid, but that is fine. That is still capable to submit. So the items required for submission you want to look at, you want to have a description of your hardware configuration and a file system that you configured. We're going to also submit the result underscore summary.txt file, also the result.txt file. And then at the end of every run, it's going to tar up your entire directory and config files into a tar file. So you want to submit that as well. It's going to look like IO500, host name, result directory. So these will change for each one of your runs. It'll have a timestamp on it. So the example for mine would be IO500, Clyde VM3, and then the date that it was run. So you want to submit those files. And for final submission, you want to submit that to the committee before the end of the competition. So general experience and kind of feedback. So in this case, There's no tuning of this benchmark parameters required, so we're not changing the INI file. So your performance will depend on the hardware and file system that you have. So your hardware that you're using to make the file system, your drives and your network, definitely want to use your high-speed network, and the file system you choose, be it NFS or any other parallel file system. So that's going to be what drives your performance. You also want to ensure that the MPI runs are configured to run over your high-speed network. That's a key thing. If you have something in the configuration or you MPI that makes a mistake and runs over to 1 gig management, it will flood it and disrupt it. So you just want to double check, and that'll bring down your entire cluster. So you want to make sure that that MPI run is configured to run over your high-speed network. You also want to be sure that you have enough space for the output data, and it's going to be about 3 terabytes of data for each IO500 run. So while it's going through, it's going to create 3 terabytes of data. If you get through the full test and you get a score, then IO500 will delete that data after every run. One thing to be on the lookout for, if the run is hung or you cancel out of the run, you may need to go in and do a manual deletion there. If you have any questions, we'll be available to help. But the normal expectation is if you start the run, it'll create files. So you need to make sure you have 3 terabytes. Then when it completes that, it'll delete those 3 terabytes. The data that it keeps isn't going to be really substantial. So, you can run multiple runs. But the thing is, if you see it's growing way beyond 3 terabytes, you got to look and see, did you cancel or did it hang anything? And you might need some manual deletion. If the IO is slow for whatever reason, you want to see if there's any other IO applications running. Main thing there is don't run your IO500 at the same time you're running your other compute benchmarks. You got to kind of keep them separate. Again, you want to run these benchmarks separately, not while the rest of the system is running. And you only need to validate results for the 6 that we chose to run in the student cluster competition. So lastly, I'm going to look at, kind of show you some results from what we run in our lab. So we have a 8-node Weka cluster, and we're using 16 compute clients. So we run a complete IO500 in this case, and these are order of magnitudes larger than the small cluster that we were doing testing on, but this is like a production scale IO500 that we could submit to the for ISC-25. But here you'll see different performance, and our score here, orders of magnitude faster because it's a production system. 112 on the bandwidth, 534 kilo IOPS on the ops, and our average score is 245 here. This small system would be in the top 20 in, I think, the most recent IO500, but this is just an example of what we would do or what we see from a complete run and a production quality. So I'll stop there, and Ophir, I don't know if we're gonna have time for questions, but this should get everybody started. We'll be available. I'll be available if you have any questions while you're preparing or at the competition.
Anyone has any questions, just feel free to say. In any case, we are listening to the Slack, so if you have any issues, just ask us on the team channel. We'll try to help, and we will be with Kevin on IC as well if you have any issues in IC, in actual IC event. Okay, so I would like to thank Kevin. Thank you, Kevin. It was very nice, very good presentation. And everyone, good luck, and prepare your pilot file system, and we'll see you at the show floor in Hamburg. Okay. Okay. I see some people want to talk. You can just unmute yourself if you want to talk.
So one of the questions we have is, since the benchmark is based on the hardware, the results be better for those with better hardware. How will the committee decide which team is getting a better score?
So you need to decide how your hardware will look like. You have a budget of 6 kilowatt to use in your competition, and that's supposed to be all your hardware you can use. You can maximize the hardware by adding more hardware, but limit to 6 kilowatts. Each decision you make will affect your runs. So if you're using GPUs or CPUs, or what kind of server, how much power it takes, how much storage to bring, it's all decisions you need to make, and bring your best best cluster that you can think to maximize your performance. It's a good question.
Yeah, and I'll add one more here. So while you're thinking about designing, you brought up a good point on, your power budget. While all of the parallel file systems are a function of the storage devices and which network. So you're gonna pick the optimal network for your compute. So it's gonna be high speed. So that kind of fixes that. So that should be fairly equal. I'd say err on the side of more smaller NVMEs. One, you want it to be flash, not a spinning disk in your systems. NVMe probably would be the best bang for buck in terms of power output versus performance. And then smaller, more disks are better than fewer large disks, if that makes sense. So those are things you could play with inside of whatever file system, be it NFS or BGFS or Lustre, those type of things. But number of disks more disks is better. So, kind of use that as something you can play with in the design of your hardware in that fixed power budget.
Okay, thank you, Kevin. So we'll continue the discussion in the Slack. If you have more questions, just let us know. We'll try to help. And if not, anyway, good luck, and see you in Hamburg. Okay, so bye-bye, everyone.